All right, so the plan for today's class is to work through section 2.2, the limit of a function, and start 2.3. These are both pretty big sections, so I'm not sure how far we're going to get into 2.3 today. Um, we might not even start 2.3, but ideally we would get a good start on 2.3, finish up 2.3 next time, and talk about 2.4 next time as well. The quote of the day today is from a movie called The Truman Show. And it's maybe a little bit older now. It's a Jim Carrey movie, but not really a comedy movie. Um, and so I don't think I'm spoiling anything. Basically, the premise is that this guy, Truman, um, he's lived his entire life on a TV set, and he doesn't know it's a TV set. It's a huge, like, constructed dome with like a little town and everything. All the people are actors. There's all kinds of hidden cameras. And um, basically, the whole premise is that this TV show has followed the evolution of his entire life until, I don't know, he's maybe in his 30s or something. Um, and at one point, I think the context is, somebody kind of behind the scenes is asking Christoph, the main guy, the mastermind, the producer, director, whatever, something about like, how does he not like realize that this isn't real? And Christoph gives this quote, which I think is really an amazing idea that we accept the reality of the world with which we're presented. It's as simple as that. And I think this idea is so important today in understanding the role of education, at least part of the role of education. I should give him the respect of putting a period at the end, get our grammar right anyway. Um, but a lot of people are asking these days, what's the value of education essentially at all, or maybe more specifically, what's the value of an educational component that doesn't directly relate to what I plan to do in my job. In other words, if you can't tell me how I'm going to directly use this to further my career, I might not see so much value in that. And I think that's a lot of what higher ed is wrestling with today, and even education in grade school and high school. Um, and I think this really speaks to the value of that. If you ask a lot of people, even folks who teach gen ed courses, what's the value of your course? Why should I take your course? A lot of times they give what I think are pretty poor answers that don't actually address the question. They might say something like, oh, it's kind of like mental exercise. Going through this will make you better at doing hard things or figuring out problems or whatever. And that kind of transfers um, to other aspects of your career or your life or whatever. Sometimes they'll give you examples for like math, like, oh, if you're ever framing a roof, well, trig is really helpful. Well, I don't know about you, but I've never framed a roof and I don't expect to frame a roof. And if I did frame a roof, I could probably get it done without trig. If I buy a Swanson speed square and, watch a YouTube video on it, probably don't need trig for that. So I feel like those are kind of blow off answers to a very serious question. I think the appropriate answer, at least in my opinion, is when we grow up, as kind of kids to teenagers, we're basically pretty much only presented with one worldview. For most people, most of the time, our family, we spend a lot of time with them. They more or less represent one worldview. Our local folks near us geographically are folks that we go to grade school and high school with. Again, mostly of kind of similar demographics, similar this or that characteristic, whatever it may be. Um, and it's easy to think that that's the extent of reality, of everybody's reality. We're presented with that reality for, 12, 15, 18 years. And we think that is all that there is to reality. And I think we know, or we at least suspect, with things being so connected these days, that there's actually a lot of different realities. That even just 2 miles down the street from where you live, there might be somebody living a completely different reality than you, to say nothing of on the other side of the globe. Um, so I think that is really the purpose of general education, of the core curriculum. At least one of the important purposes is to introduce you to some other realities, to some other modes of thought, to some other aspects of different cultures. Um, and when you realize that there are different realities, that I think fundamentally brings a different perspective to your life and how you make decisions and how you view and interact with other people. So I think that is really the value of the the components of higher education that are not directly career related. Now, don't get me wrong, there's a very important component of higher education that is directly career related, right? I mean, if you know, a lot of you are going for engineering or computer science, something like that, like you want to be able to do that career when you enter that career field. That's not to be overlooked. But I think it's two pieces that contribute to the whole, not, you know, one important piece and one vestigial piece that, oh, why do we still have that? Um, and actually, I think it's a little bit of a shame that we're questioning this so deeply these days, because if you think about human history for thousands of years, pretty much nobody had the ability to study things that weren't directly related to their career. You know, if somebody was going to be a tanner in 1542 or whatever, they didn't have the means or the time or the even the lower level education to study philosophy or mathematics or anything like that. They were taught by their father, who was taught by his father how to tan leather or whatever it is that they do, and that was what they could do. And maybe in the last 100 years or so, we've gotten to a point where pretty much everybody across society, at least in the US and many similar countries, has the opportunity to study so many of these things that used to be restricted to kings and princes and aristocrats and those kind of folks. Um, and I think it will be a real shame to see that slip away in favor of just career training, kind of going back to, you know, say something along the lines of pre-1800s or pre-1700s. Um, so that's my that's my argument for, you know, why people not going into engineering or something that will use it directly should take math, or why people going into engineering or computer science should take your English course seriously or your art history course seriously. There is more to life than just career. Okay, so that's the quote of the day today. Um, so moving into the more technical side of things, and you know, as calculus, this is more of a kind of major career-based course. So discussing the limit of a function. And just to quickly remember what we talked about last time. So last time we discussed this idea of the tangent and velocity problems. And we kind of said, okay, we want to generalize some ideas from, let's say, something like basic algebra, basic geometry with straight lines, something like slope of a line. Or maybe we want to generalize something like the average value of or average value of a function, average speed over a time interval, and be able to talk about, say, speed at a particular point in time, or slope of a tangent line at a particular point on a function. Naturally arising from that came this idea that we kind of make a secant line by choosing the point of interest alongside one kind of other point. And then we let that other point get closer and closer to the point of interest, kind of moving along the curve, to get secant lines that are closer and closer to that tangent line. Or maybe in a different context, we would take a time interval, maybe 2 seconds, and we'd look at the average velocity over that time interval, and we would shrink that time interval down smaller and smaller, keeping the the time point of interest in that interval, of course. And we would look at that average, look at that average speed. Sorry, my allergies have been acting up the last few days for some reason. But anyway, we would look at that average speed over a smaller and smaller time interval, still containing our point of interest. And we would investigate either the slopes of those secant lines or those average speeds, that progression. And we would ask, well, does it look like those numbers kind of settle on a particular number? And keeping in mind, of course, that I could, for my secant line, I could choose my second point either to the left of the point of interest or to the right. So I might want to check both directions and make sure that nothing unreasonable is happening. We saw some counterexamples where we had, say, an absolute value function with where depending on whether you approach from the left or the right, you might have got different answers. And we might say that in that case, that's not too satisfying. We're going to say that the answer doesn't exist in that case. Or with the average speed, we could choose a time interval that is to the right of our point of interest or to the left of our point of interest, or maybe even straddling our point of interest. So we looked at some of that last time. So that was the setting that we're moving into 2.2. And we want to formalize this idea, right? That seems very non-mathematical to just say kind of like plug in a bunch of inputs, look at a bunch of outputs, and make a guess at what you think it goes to. I mean, if it goes to an integer number, then maybe we can make a pretty reasonable guess, but what if it goes to some crazy irrational number? So let's formalize this idea. And we formalize this through the idea of a limit of a function. So definition. The notation that looks like this. I'm trying to select just this left-hand piece and it's not cooperating, but the notation limit x goes to a f of x equals L, a real number. So this is just an element of the reals, or just saying that it's a real number, not some complex number, and also importantly, not plus or minus infinity. We would say that the limit of f of x as x approaches a is L. And what does this mean? This means that we can make the output of f of x, the output of our function, as close as we like to this limit L, real number, by taking values of the input x sufficiently close to a, and very importantly, but not equal to a. Remember, when we were thinking of our secant line, we needed two distinct points to make a secant line. If I chose my quote second point to be the exact same point as the first point, I don't get a secant line. I can put infinitely many lines through that with all kind of different slopes. If I chose my time interval to be of zero width, then I don't have an average velocity that I'm able to calculate. I get a 0/0 kind of deal. So I want to look at what happens to the outputs of a function when I plug in inputs that are close to the limiting value of interest, but not equal to that value. Very important point of this. So for instance, if I look at limit x goes to 0 of x squared, if I come over here, I'm going to use this function calculator on Desmos. I think this is like some random person programmed this, but it seems to work. So I'm using this. I still can't get my Wabbit emu, which is just a hilarious thing to say. I don't know. I still can't get it to work. I re-downloaded a fresh copy, and so I have to investigate why it's not working. And hopefully I can make it work because it really is the best solution to this. But here, if I look at my function f of x equals x squared, and I want to plug in values close to 0, well, again, I don't want to plug in 0, so I'm just going to get rid of this. But if I plug in negative numbers close to 0, so say negative 0.1, gives me an output of 0.01. Negative 0.01 gives me an output of 10 to the minus 4. Negative 0.001, output of 10 to the minus 6, and so on. And of course, I would get the same thing for positive numbers because x squared is an even function. So I think that I hypothesize that as I plug in values of x closer and closer to 0, the output of x squared also gets closer and closer to 0. Therefore, I might feel comfortable saying that the limit as x goes to 0 of x squared equals 0. So what about looks like the the equation editor isn't displaying quite right here, but limit x goes to 2 of x cubed. So again, if I have the function x cubed, I can go through and do this kind of thing, but I can also represent this function graphically. So this is the point that I'm interested in, 2 comma 8. It looks like I got my 8 a little bit high there. But I want to think of this really as an open circle, an open point there. Because again, I don't want to plug in the value of 2 when I'm in a limit. But I can imagine what's going to happen as I pick inputs that are closer and closer to 2, either from above or from below. I see pretty clearly my outputs are going to get closer and closer to 8 from above when my inputs are above, or from below when my inputs are below. I might look at the graph and feel comfortable saying that this is 8. I might be tempted now to think, oh, well, all that a limit is just plugging in the limiting value into the function. Again, we have to be very careful. Number one, because our definition specifically precludes that. And number two, we're going to see that we generally don't want to do that anyway. In these very simple limits, it turns out that doing that is okay. We have a theorem later on that says we can do that in some cases. But in the limits that we're going to be interested in for the most part, things related to like the secant lines going to the tangent line, or like the average speeds going to the instantaneous speed, that's not going to be a good idea. We're not going to want to do that in those types of limits. And that's really where we're headed with this. So we want to stick closely to the definition here, not get too hand wavy or not get too sloppy with our details, because those details are going to actually be really important later on. So it might seem a little pedantic at this point, but there is a reason for it. Here I have the constant function 3, limit x goes to 0 of 3. Maybe I'll draw it in blue so that we know which one is the function and which one is the real line. My point of interest is 0, so maybe I'll turn that into like an open circle. And again, I can clearly see that as I choose inputs above 0 that get closer and closer to 0, I get outputs that, in fact, are always exactly equal to 3. As I choose inputs below 0 that get closer and closer to 0, again, I get outputs that are all exactly 3. Here, I probably feel quite confident in saying that this limit is 3. Give me 1 second. Okay, sorry about that. I don't know why I'm like suddenly allergic to my office or something. Um, okay, let's look at the function 1 over x. Limit x goes to 1/2 of 1 over x. Since I'm only worried about values of x that are near 1/2, I can restrict myself to just the positive side of things and just draw this positive piece here. So I'll do kind of an open circle at 1/2 comma 2, 1 over 1/2 being 2, of course. And again, I can imagine looking at my graph instead of a table, that if I have numbers that have inputs that are above 1/2, getting closer and closer to 1/2 from above, then in this case, I'm going to get outputs that are below 2, but working their way up to the number 2. And likewise, if I have numbers that are below 1/2 on the input side, working their way up to 1/2 on the inputs, I'm going to get numbers that are above 2 on the outputs, working their way down to 2. And again, here I probably feel comfortable thinking that this is 2. This is a function that we looked at last time. and we came up with what we thought was the answer for it. But since I really don't know how to graph it, it's going to be kind of a messy graph. Let me use the tabular method over here. Let me shift this over just a little bit. There we go. So I need 2 sine of pi x plus 3 cosine of pi x. And I'm looking for what happens as my variable goes to 1. So I might look at, say, 1.01. I see an output of negative 3.06, negative 3.006 when I go 1.001. I add a couple more zeros, I get a couple more zeros in the output. If I go to 1 minus this, right, as I approach 1 from below on the input side, I see that I start at negative 2 point something and work my way up to what looks like negative 3. So when I approach an input of 1 from below, I approach an output of negative 3 from below. And when I approach an input of 1 from above, I approach an output of negative 3 from above. I feel pretty confident that this limit ought to be negative 3. We have something like this, limit x goes to 0 of cube root of x. The cube root of x looks, whoops, draw that a little better, looks like this. It looks like x cubed flipped over the line y equals x. Now we might remember this from last time, and we said if I tried to draw secant lines, say where my point of interest was at x equals 0, and work my way toward a tangent line, things like seemed to kind of blow up. It didn't really work too well. Now note that the limit of the function is a different question than the limit of some other function that is the slope of secant lines for this function, right? So I have this function, cube root of x. If I constructed the difference quotient, so for some deviation h away from 0, the slope of the secant line, that's a different function. It's related to cube root of x, but it's not cube root of x. So something related to this blew up last time, but this doesn't blow up. We can clearly see that as I choose inputs, they get closer and closer to 0. I'm getting outputs. They get closer and closer to 0, both from the positive side and similarly from the negative side. This limit is just fine, it's 0. Now, if I try to find the slope of the tangent line at 0, that's where things blow up. Because that slope, as I take my one point of interest, 0, 0, and another point of interest, say off to the right, and I move that second point close to my original point of interest, the secant lines get steeper and steeper and steeper without bound. And my tangent line would be something like a vertical line. Similarly, if we tried to find something like the slope of the tangent line for this absolute value function near 0, we saw that that was a problematic question to answer. We weren't able to get a good answer to it. But if I'm just asking for the limit of the function itself, that's a different question. If I plug in inputs that are above 0, but heading towards 0, I get outputs that are above 0 heading towards 0. And likewise, if I plug in inputs that are below 0, but heading towards 0, I get outputs that are above 0 heading towards 0. In both cases, my outputs head towards 0. This limit is just 0. Now, again, if I was to like take a point of interest, a second point, draw a secant line, I'm going to get different results for the slope of that secant line, whether my second point is to the right or to the left of zero. So we have a problem there with finding slopes of secant lines and tangent lines and so on, but finding the limit of the function itself, not a problem. Be really careful that those are two different questions. What's the limit of the function itself versus like what's this limiting value of the slopes of the secant lines turning into slope of a tangent line. So what about something like this? Limit t goes to 0 of square root of t plus 4. What does this look like? Well, I know that for square root, I can only plug in non-negative numbers. So I can only plug into this function values of t that are bigger than -4. And when t equals -4, that's square root of 0, which is 0. And when t is 0, I get square root of 4, which is 2. So I get something like this. I don't want to plug in that value, but it's going to look more or less like that. And again, I'm interested in what happens around t equals 0. If I plug in inputs that are, say, below 0, getting closer and closer to 0, I get outputs that grow up to 2. And if I put in inputs above 0, getting closer to 0, I get outputs that decrease to 2. I think this answer is going to be 2. Now, again, so far you look at, I think, every one of these, and you notice that the result of the limit is just what you would get if you chose to plug the limiting value into the function inside the limit. So again, you might ask, well, why can't I do that again? And aside from me giving a hand-wavy answer about what we're going to see in the future, consider a problem like this. F of t is 1 when t is non-zero and it's 0 at 0. Compute limit t goes to 0 f of t. What does f of t look like? F of t has height 1. Anywhere other than an input of 0, it has height 0 at 0. Note that f of 0 equals 0. Is limit t goes to 0 f of t equal to 0 then? Actually not. Let's go through that same process. I plug in some inputs on my right side of 0, getting closer and closer to 0. I notice that my outputs all have exactly height 1. I plug in inputs to the left of 0, getting closer and closer to 0. I notice that my outputs all have exactly height 1. In fact, if I forgot about this, what the behavior at 0, this looks exactly like my almost trivially simple problem, limit x goes to 0 of 3. What's this limit? This limit is 1. Well, I shouldn't cross that out. It's not wrong, but this is not the limit. The limit is 1. It's not 0. Because the behavior near 0, but not at 0, is an output of 1. If I plug in any number that's close to 0 but not equal to 0, or really any number not equal to 0 for that matter, I get an output of 1. So my outputs are always 1, near 0 but not equal to 0. What about a function like this? Limit x goes to 0 sine 1 over x. Now, if we try to plug in a 0 here, well, what does that even mean? We're not really sure. Sine of 1 over 0, that's undefined. So f of 0 doesn't exist. Does that imply the limit doesn't exist? Not necessarily. Let's try to understand this limit a little bit. Let's actually graph it over here, I suppose. So let's take a look at sine 1 over x. And let's zoom in quite a bit. And we noticed, oops, a little too far. We noticed that it kind of oscillates faster and faster as we get closer and closer to 0. So I see some behavior, something like this. These peaks and valleys should all be the same height, but it does look like it's kind of confusing to tell what happens really close to 0. Well, one thing I can ask is like, where do I get, I see that I get some outputs of like, say, height 1, right? Where do I get outputs of height 1? Well, I get a maximum of sine whenever I'm plugging in, say, pi over 2 or 2 pi plus pi over 2 or 4 pi plus pi over 2. So if 1 over x equals k pi 2k pi plus pi over 2, where k is an integer, then my function, my output is 1 in that case for those choices of x. Or in other words, sine of 1 over x equals 1 when x equals 1 over 2k pi plus pi over 2, where k is an integer. And in fact, as k gets larger and larger, so as k gets larger, I'm not going to use that notation yet. We didn't really introduce it, but we see that x goes to 0. I see that as k gets larger, the denominator of the fraction gets bigger and bigger, and my input x gets closer and closer to 0. So this does kind of satisfy the limiting condition that x is heading towards 0. There's no k that I can plug in that gives me exactly x equals 0. So when I plug in different values of k, say larger and larger integers, I do get closer and closer to 0, but never exactly 0. So I do satisfy that constraint of the limit. And I see that the output is always 1. So what I've done is I kind of think of it in a sense like I'm trying to cross a river, and I've kind of have some stepping stones that I'm choosing to step along. In this case, I choose to step along the stepping stones that look like 1 over 2k pi plus pi over 2. And the value at every one of those stepping stones is an output of 1. So we might just say, oh, okay, it seems like our limit is 1. Let's be a little careful though. Can I get a different output? Well, sure. I mean, I guess I could get outputs of, say, 0. And looks like I could get that output at several different places. What are all the inputs that give me an output of 0? Right. So my question is 1 the limit, because this seems to kind of satisfy the criteria for the limit? Well, if 1 over x equals what? Equals, let's say, m pi, for m an integer, well then, unfortunately, sine 1 over x is 0. Sine of m times pi, where m's an integer, is 0. So sine of 1 over x is 0 for x's that look like, well, it's what? X would be 1 over m pi, where again, m is a integer. As m gets larger and larger, x goes to 0 as before, putting a bigger and bigger number in the denominator. That's making the fraction smaller and smaller, of course. X is never going to be equal to 0 for any choice of m. So unfortunately, what I've done is I've come up with kind of two candidate limits. I've given an argument that if the limit exists, it has to be 1. But I've also given an argument that if the limit exists, it has to be 0. And in fact, I could give an argument for whatever number I want between -1 and 1, including the endpoints. If you wanted to come up with an argument for if the limit exists, it has to be -1, or if the limit exists, it has to be, square root of 3 over 2 or something like that, you could come up with such arguments. Well, these are clearly contradictions, right? I can't say on one hand, if the limit exists, it has to be 1, and on the other hand, if the limit exists, it has to be 0, and proceed forward constructively. This is a contradiction. So this limit, we say, does not exist. So here, the function value at 0 didn't exist, and the limit also happened to not exist. Is that always the case? Interestingly, no. If we look at this very similar function, but ends up being quite a bit different, limit x goes to 0 of x times sine of 1 over x. Well, here, again, f of 0 does not exist. We can't plug in 0 because we would have a sine of 1 over 0, and we don't know what to do with that. So f of 0 is undefined. If I look at the graph of this, well, sine of 1 over x looks like this, but x times sine of 1 over x actually looks like this. I mean, I actually know that x sine of 1 over x is between, on the graph, y equals x and y equals minus x, because sine of whatever has to be stuck between -1 and 1, right? So this multiplier on x has to be a number between -1 and 1. And we can evaluate it everywhere other than at x equals 0. So we have no problems except at the point that we're not allowed to look directly at anyway. It's, you know, that x equals 0 is excluded from consideration by the limit. So in fact, we're kind of stuck between a function that looks like this and one that looks like this, is I have inputs that get closer and closer to 0. My outputs have got to get closer and closer to 0. And if we didn't believe that, we could do some experimentation with a table, say an input of 0.1 yields an output of -0.05. If I move that 1 over one more decimal place, I get an output of -0.005. Another one, I get 10 to the -4, -3 times 10 to the -5, 10 to the -7, 10 to the -8, 9, 10, and so on. And now we get something similar if I was looking at the negative numbers. So in fact, I've shown that this limit is 0, or I've argued, I suppose, that the limit is 0. The limit as x goes to 0 of x times sine 1 over x does exist, and it's 0, even though the function value doesn't even exist at 0. Again, these are the nuances that we can now handle because of this all-important restriction in our definition being not equal to the limiting value. Any questions so far? Okay, now let's look at the Heaviside function. I used to think it was like the heavy side function, like one side is heavier than the other because of how it looks. It's like output of 1 for t bigger than or equal to 0 and output of 0 for t less than 0, but it's actually named after a physicist. Oliver, I think was his name, Heaviside. So the Heaviside function. So for t is less than 0, it has an output of 0. For t is bigger than or equal to 0, has an output of 1. It looks like this. Let's consider some different limits. Limit is, say, t goes to 2. Well, again, if I think of inputs getting close to 2, the outputs are always exactly at 1. We don't plug in 2, but as we plug in inputs closer and closer to 2, the outputs are always 1. As long as I don't stray too far to the left, if I plug in -1 or something, then I get an output of 0, but as long as I stick pretty close to 2. This is another really nice feature of limits. Because we're staying sufficiently close to the limiting value, I can restrict my domain to as small of an open interval as I want around that value when I'm just looking at the limit. This limit is a local property, so I can just kind of pretend this left-hand side doesn't exist because 2 is kind of firmly in the right-hand side. I can just consider an open interval, say of width 1 or width 2 or something surrounding 2, and I can stick to this side where just h of t equals 1 for my interval of consideration. This limit, of course, is just 1. Limit as t goes to -1, similar argument. Because I'm just looking at the limit, I'm looking at what happens locally to inputs of -1. I can restrict myself to just looking close to -1, and I see that my outputs, my function is just basically a constant function here of height 0. My outputs are all going to be 0 anywhere in that interval. Now, if I'm looking at a point of interest at t equals 0, any open interval that I draw around those inputs, it's going to have some of the one half of the function and some of the other half of the function. So I can't just restrict my domain and get an answer here. Well, one thing that I can do is I can just look at what happens when I plug in inputs that are above 0, getting closer and closer to 0. I get outputs that are exactly 1. So from this perspective, we're saying if the limit exists, its value has to be 1. But on the other hand, I could plug in inputs less than 0, working their way up to 0. And here, I would have outputs that are all 0. I would be saying that if the limit exists, it has to be 0. Approaching from the right, if the limit exists, it has to be 1. Approaching from the left, if it exists, it has to be 0. Again, there's a contradiction here. This limit does not exist. Again, even though h of 0 exists, h of 0 is just 1, but the limit isn't 1. The limit doesn't exist because the value that the limit would have to be is different depending on the perspective, whether I look at it, say, plugging in positive numbers, working my way down to 0, or negative numbers, working my way up to 0. Any questions so far?
Is there always one unique, like, can a function have more than one limit? Or is that always going to be one limit?
Um, sorry, I had a little trouble hearing you there.
Yeah. Is it always going to be like one limit per function, or is it possible to do, are they going to have more than one limit?
Oh, okay. Yeah, so good question. If we're saying if we're using this notation, then we're saying that the limit should be at least at this point just one number. Uh, so we want to be able to replace this statement, limit x goes to a f of x, with a number and say that those are equivalent. So if we have, it's similar to the idea of like functions and the vertical line test, similar kind of idea. That if I have a function like this, we're happy with that because each input yields at most one output. But if I have say a relation like this, an input can yield multiple outputs, I wouldn't call that relation a function. It's kind of a similar idea that um, for a limit to be well defined, it's only well defined if it has a single value that kind of all perspectives agree on, so to speak. And in a case like this, or in a case like this, because there's disagreement, from one perspective, the limit should be this number, and from a different perspective, the limit should be this completely different number. That's when we say the limit does not exist. Yeah, so kind of the short answer is if a limit exists, it only has one value. And if a limit seems to have different values depending on perspectives, then we say the limit doesn't exist. Yep, good question. Any other questions? Okay, give me 1 second here. Okay, so moving on to one-sided limits now. So we can define one-sided limits like this. Let me zoom in a little bit so you can see this a little bigger on your screen. We have a very similar looking notation. Limit x goes to a, f of x equals L, a real number, except that here our a has a little superscript plus. So this a that's kind of small below the limit has itself a superscript that's a plus sign. So we would say this something along the lines of the limit of f of x as x approaches a from above or maybe from the right is L. And what this means is that very similar to the definition of a general limit from above, we can make the output of f of x as close as we like to L by taking values of the input x sufficiently close to a, but strictly greater than a. So not equal to a, but also not less than a. And we can make the analogous definition for limit x goes to a from below, where that a has a little superscript minus. Limit x goes to a from below, f of x equals L. That would be plugging in values sufficiently close to a, but strictly less than a. So not plugging in a, but also not plugging in any number greater than a. So we actually do see that that kind of resolves the Heaviside issue. Limit t goes to 0, h of t doesn't exist. But we note that the right-hand limit, as t goes to 0 from above, as I approach 0 from above, my outputs are all 1. This is just the value 1. And my left-hand limit is the value 0. So even though I don't have an overall limit for the Heaviside function at 0, the left-hand limit exists and the right-hand limit exists. Now they don't happen to be the same number, and that's where the discrepancy is. As kind of a side note, this limit x goes to 0 sine 1 over x, approaching from one side or the other doesn't fix that, right? For instance, we could plug in only positive integers in these constructions, and we would still get the same contradiction. Or we could plug in only negative integers and still get the same contradiction. It's not the one-sided limit on one side disagreeing with the other side that's causing the problem here. It's really that we're kind of like, we almost have like a smear of, you know, function drawing or whatever near zero, not something that's nice and kind of clean like this. So the one-sided limits at zero would not exist for this, and the overall limit does not exist. But for the Heaviside function, it's nicely enough behaved at zero that the one-sided limits exist, but because they disagree on their value, the output value, the overall limit does not exist. We have a nice theorem that the overall limit exists and is equal to a real number L if and only if both of the one-sided limits exist and equal the same number. And so we see the problem. The Heaviside limit, or the Heaviside function, has limits at zero, one-sided limits at zero that both exist, but they equal different numbers. So therefore, the overall limit does not exist. Are there any questions so far? Okay, let's look at an example. So let's consider a limit x goes to a of f of x. And here we're going to look at the left-hand limit, the right-hand limit, and the overall limit at each of these integer points 0 through 6. So I'm going to write a is like 0 minus, 0 plus, and 0 to represent kind of the left-hand limit at 0, the right-hand limit at 0, and the overall limit at 0. And we're just going to kind of investigate each of these. Now, right away, the left-hand limit at 0, well, this doesn't exist. So the input is a, and the output is what is the limit x goes to a f of x. Clearly, this doesn't exist because we can't even plug in, at least according to what we see here defined for the function, we can't plug in inputs that are to the left of 0 and get anything meaningful as an output. The right-hand limit, though, if I plug in values that get closer and closer to 0, I see that my outputs get closer and closer to 2. So my right-hand limit of 0 is just fine, it's 2. Now, note that f of 0 doesn't exist, right? F of 0 is undefined. This is an open circle, but the right-hand limit is 2. The left-hand limit doesn't exist, the right-hand limit is 2, the overall limit doesn't exist. Let's look at x equals 1. Approaching from below 1 on the inputs, our outputs work their way down to 1 on the output side, and approaching above 1 on the inputs, same thing, our outputs work their way down to 1 on the input side. So the left-hand limit is 1, the right-hand limit is 1. Those two limits both exist and agree. The overall limit is 1. So now let's look at x equals 2. Does the left-hand limit exist? Yeah, it does. The outputs work their way up to 2. The left-hand limit's 2. Does the right-hand limit exist? Yeah, sure. The outputs work their way down to 1. Does the overall limit exist? Does not exist because 2 is not equal to 1. Both of the one-sided limits exist, but they don't equal one another. At 3, note that f of 3 equals 1, but the left-hand limit is 2, the right-hand limit is 2. They both exist and are equal. The overall limit is 2. Note that the overall limit is not f of 3, which is 1. Looking at 4, f of 4 doesn't exist, but the left-hand limit, remember we're not plugging in 4 anywhere in the limit. The left-hand limit is we plug in values that approach 4 from below, we're getting outputs that get closer and closer to 1. The right-hand limit at 4 is also 1. These both exist and are equal. The overall limit at 4 is 1. Looking at 5, we have this kind of cusp or corner here, and we saw that caused problems with things like tangent lines. But the question we're asking now has nothing to do with the tangent line. We're just asking for the limit of a function. So we don't want to jump too far ahead or think too much in terms of tangent lines and so on. We're just asking for the value of a limit. As I approach 5 from the left on the input side, my outputs approach 2. My left-hand limit's 2. Same with my right-hand limit, it's 2. These both exist and are equal. My overall limit's 2. And then maybe I'll come up here. At 6, my left-hand limit is 1. My right-hand limit, well, that doesn't exist. I can't plug in values above 6 and get anything reasonable for an output. The overall limit doesn't exist, but the left-hand limit does. Any questions so far? Now I want to note a cautionary example here. Let's consider the limit x goes to 0, sine of pi over x. So we know the sine of 1 over x kind of didn't work for x going to 0. What if I have sine of pi over x? I mean, the graph looks basically the same. Now, what inputs might, if I was just kind of going to try some inputs, what inputs might I try? You might look back at this one and say, well, would I ever try a bunch of inputs to look like this and kind of, think that the output was 1 everywhere and write down that the limit was 1 mistakenly? Maybe not for something like this. You're not likely to choose as inputs things that look like this or even things that look like this. But you might be likely to choose, say, the number 1, giving an output of 0, or 0.1, but 0.1 also gives an output of 0, or 0.01, giving an output of 0, or 0.001, giving an output of 0. So here, if my selection of x is, say, 1, 0.1, 0.01, 0.001, I see I get an exact output of 0 for all of these. Or if they were negative, negative 1, negative 0.1, negative 0.01, negative 0.001, still 0. Looking at this table, these are exactly the kind of tables I saw above that convinced me very strongly that this was 0 and I was done with it. But clearly that's not the case, right? This suffers from exactly the same problem as my one up above. If I used, I don't know, say 0.3, I get an output of negative 0.866, 0.03, negative 0.866, 0.003, negative 0.866, right? So that negative 0.866 is clearly not the same number as these zeros. But if I just keep incrementing by, say, one decimal place, it's going to look like, if I had chosen this instead, it would look like my limit was negative 0.866 or so. So we would like to build more algebraic structure behind this so that we're not just kind of drawing out tables or looking at graphs and kind of taking a shot in the dark, especially when we get to more complicated looking limits, which are the kind of limits that we're going to get when we're looking at slopes of secant lines and difference quotients or like average velocities. Those are going to be more complicated limits than just just ones like the ones that we saw up here. Any questions so far? Okay, then moving on to infinite limits. So if we have a notation like this, limit x goes to a f of x equals infinity, this is a very strange looking thing because we very rarely say something equals infinity. We might put infinity in an interval to signify that that interval kind of never ends on that side. But what do we mean by this? We can actually think of this whole thing basically as a notation. Kind of up above, I was really thinking, it's not letting me select it the right way, but I was really thinking of kind of this as a notation, and then I could say it truly is equal to some number that's a real number. That the right-hand side of the equal sign and the left-hand side of the equal sign are the same number. I can maybe think of this thing kind of overall as an idea, or kind of more abstractly, the left-hand side of the equals and the right-hand side of the equals kind of represent the same idea. What do we mean here? The meaning of this notation is that we can make the output of f arbitrarily large positive by taking values of the input x sufficiently close to a, but again, not equal to a. As a side note, there's a little nuance here that's not captured in this definition that we might clear up in section 4. We can make a similar notation for limit x goes to a f of x equals negative infinity. The only thing that changes is arbitrarily large positive to arbitrarily large negative. Again, there's a little nuance in this definition that we haven't taken care of. We'll revisit that a little bit later. So for instance, I could look at limit x goes to 3 of 1 over x minus 3 squared. What does this function look like? One over x minus 3 squared, taking the limit as x goes to 3, so I'm interested in what happens near a 3. It looks kind of like this. I can see no matter how far I zoom out, I never like reach a cap or anything like that at 3. It doesn't, it doesn't do something like this. I have a vertical asymptote. So it's not like this, that if I just zoom out far enough, I'll see the top. It's more like this with no top. So if I plug in values closer and closer to 3, let's say 3.1, 3.01, 3.001, my outputs just keep getting bigger and bigger in the positive direction. Or I could do the same thing from the other side. If I plug in out or inputs like 2.9, 2.99, so on closer and closer to 3, I get outputs that just get bigger and bigger positive. The closer that I plug in the closer that my input that I plug in is to 3, the larger positive the output is. We can say this limit is infinity. What about a limit like this? So this function, what does anybody know what this function is? What it represents?
That's the Lorentz function.
Yeah, exactly. It's the Lorentz factor from special relativity. And it's kind of the correction in some sense, the relativistic correction uh for when your speed is say close to the speed of light, then v over c all squared, when your speed is like 10 miles an hour, that's effectively zero. But if you're going, 99% the speed of light, then v over c is like 0.99 and v over c squared is like 0.98. Well, then this becomes an issue. What happens is my speed, v, approaches the speed of light from below. What happens to the Lorentz factor? Well, as v goes to c from below, I notice that v over c goes to 1 from below. Or I can think of this function as, and this limit as being equivalent to the limit as, let's say, x goes to 1 from below of what? This would be 1 over root 1 minus x squared. As x goes to 1 from below, what happens? My denominator inside the square root, this 1 minus x squared, gets closer and closer and closer to just 1 minus 1 or 0. Square root of 0 is 0, 1 over 0. That blows up. I know this is an even function because the only place I see an x, it's squared, so it's going to be symmetric left to right. If I doubted any of this analysis, I could just come over here and plug it in. F of x is 1 over 1 minus x squared. What happens is I get closer and closer to 1. I guess I have to zoom in to kind of show you where 1 is. It's like here-ish. We can see that we're just getting steeper and steeper. Or I could look at this tabularly. What happens is I plug in values like 1 point, oops, can't go from that side, 0.99, 0.999. As I keep approaching 1 from the left, I see I get outputs that just keep getting bigger and bigger and bigger. Kind of for all of those reasons, the more hand-wavy heuristic reason, the graphical, the tabular, we see that this limit is infinity. Why do we always say like you can't go faster than the speed of light? Well, because you'd have to go the speed of light at some point, and your length contraction and time dilation and all of those crazy things would, I guess, be infinite at that point, and things kind of blow up at that point. So if you want more details on that, ask Professor Farina, because from that point on, I can only tell you what I've gotten off of Star Trek or something like that. But right, there's always like well, you can't go the speed of light, but if you go past the speed of light, then this doesn't blow up anymore or something. I feel like that's probably uh not real physics, but I don't know for sure. Who knows? Physicists have all kinds of really cool models and cool ways of thinking about things. Okay, so any questions on anything in 2.2? So I know it's a lot of material, just the amount of material is a lot, but really it's all building off of this fundamental idea, the idea of a limit. The really important idea of a limit is we're plugging in values that are really close to the desired input and looking at the outputs, but all importantly, we're not plugging in the value of the limit. We're not plugging in the value of the limiting input. Sometimes it seems like that kind of works and like things don't really break, but I hope I've given enough cautionary tales to show that we don't want to just rely on that. We don't want to just plug in the value if we can and everything doesn't explode, because we can get the wrong answer pretty easily. Okay, so if there are no questions, then we're going to move on to 2.3 using limit laws. And I don't particularly like the phrase laws. I like the phrase properties. When I think of laws, I think of like things that I'm not allowed to do. Like there's a law that says you can't drive more than the speed limit and things like that. Um, they're kind of restrictive and they like limit my options. Maybe in things like the law of gravity or something, maybe is a bit of a different perspective. But when I think of properties, these are ideas that I can leverage. They actually free me up. I have some ways of making a guess at what I think the limit might be. If I build up some properties, this is really just a big theorem, then I have more ways of trying to figure out what the limit is. Maybe I can even get myself to a point where I'm not guessing what the limit is, but I can really formally mathematically prove that the limit is this number. I mean, really everything we've done up to this point, this is all a hand wavy argument. This is all essentially guesswork, either based on a picture or based on a table. Sometimes it's better guesswork than other times, right? Sometimes we feel very confident about a number, and other times we might say, I kind of think it's that number, but I'm not 100% sure. Who knows that, that say, where's a good one? The output of this, who's to say that it's not like 10 to the minus 100 or something, that we just didn't go quite close enough to an input of 0 to see that it really settles down to some output that's not exactly 0. But now we're moving into the formal mathematical side of things, where we can actually say I can prove the limit is exactly equal to this number. What are some properties? Well, first off, the limit is linear. What do I mean by that? I mean that if I take, under the assumptions that the limit of f of x exists and is a real number, same with the limit of g of x, and that c is a constant. If I take the limit of the sum of two functions, that ends up just being the sum of the limits. So limit splits sums apart, or in a sense, the limit distributes over sums. And constants come outside of limits. The limit of a constant times a function is the constant times the limit of the function. The constant can just kind of, factor out in front of the limit. These two things together, when we have these two properties that apply to some operation, whatever it is that we might be doing, we call that linearity. If it splits sums apart, and if a constant can come out, those two things together, we call linear. So we have linear operators and linear operations and things. This is a very important idea because the main two operations that we'll see throughout calculus, the derivative and the integral, they're both linear operators. They share a lot of these same properties. Now, not all of the same properties. For instance, this property C, is not shared by them, but they share some of these same properties because they also are linear operators. So the limit splits sums apart, constants can come out. The limit also splits products apart. As I mentioned, we have to be careful because we'll introduce the idea of a derivative at the end of chapter 2. We'll introduce some properties of derivatives in chapter 3. And we might be tempted to just kind of port all of these same properties of limits directly to derivatives. That doesn't work. The easiest example is C here. The limit of the product is the product of the limits, but that doesn't work for this idea called the derivative that we'll see coming up shortly. The limit of a function to a power, the power can come outside of the limit. Roughly speaking, if you think of n being a positive integer, you can just think this is f of x multiplied by itself n times. We split all those apart using property C. And then we just kind of combine them back together to get the limit to the nth power. And my parentheses here are a little wonky. Let's get rid of that parenthesis. Okay. Had an extra parenthesis in there, but this is the whole limit x goes to af of x, all to the nth power on the right-hand side there. And we also have some limits down here, E, F, and G, some specific ones that the limit of a constant is the constant, or more precisely, the limit of a constant function, a function that has the same output for every input, is just the constant number that is the output that you get for any input. Limit x goes to a of x is just a, and limit x goes to a of x to the n is just a to the n. We have a corollary to this theorem. A theorem is something that, needs to be proven. We haven't proven this. Well, we might prove a couple of these things in section 4 when we talk about limits more formally. But for right now, we're working with this without proof. A corollary is something that kind of, given this theorem, if we can assume the results of this theorem, then a corollary is a new theorem, but it kind of like follows pretty easily from a theorem that we just proved. So that's what's meant by a corollary. And a lemma is kind of a mini theorem that you use to help prove a bigger theorem. So these are all different kinds of theorems. They all basically mean the same thing as theorem, but a theorem is kind of a big, thing that takes a bit of work to prove. A lemma is kind of an easy theorem, an easy proof that helps me prove a bigger theorem. And a corollary is kind of an easy result of a theorem. It's an easy kind of theorem that follows from a previous larger, more difficult theorem. So corollary, for instance, if f is a polynomial, then we actually can do limit x goes to f of x equals f of a. We can do the plug-in thing that we wanted to do above if f is a polynomial. Well, what does that mean? If f is a polynomial, that means it's like a1, or let's say a naught plus a1x plus a2 x squared and so on plus an x to the n. That's what f is if it's a polynomial. The a's are all constants and the x to the powers are just power functions. But I know that the limit of this, well, the limit of the sum is the sum of the limits, property A. I know the constants can come out of limits, so all the a's can come out front of each of their limits, property B. Limit of a constant is a constant, so this is just a naught plus a1 limit of x, and so on plus an limit of x to the n. I'm not writing this super neatly because I think we kind of see where this is going. I hope so anyway. And the limit of each of our power functions, we just do the plug-in thing for the power functions. We just replace x to the n with a to the n. And unfortunately, I guess I have a bunch of a's floating around. The a subscripts are the coefficients from the polynomial, and the a's themselves, like the a or a to the n, are the limiting value. And this is just f of a. So if this is f of x. We also have a quotient property. We need to be a little bit careful about it, but we have limit x goes to a of f of x over g of x equals the limit of the quotient equals the quotient of the limits. I like to split this one out because we have to be very careful with this one. This is true so long as the resulting limit in the bottom is not 0. If limit x goes to g of x is 0, or of course, if either of the individual limits don't exist, but by assumption up here, they both do. But in particular, if m from above is 0, then this property doesn't work. Why do I want to make such a big deal about that? Well, again, because when we move into talking about the derivative, talking about that limit of those slopes of secant lines or the limit of those average speeds, those kind of ideas, we effectively always end up with wanting to take a limit where if we tried to apply this quotient property, we would get a 0 in the bottom. And students can be easily misled and think, oh, I set up the limit of this difference quotient, but when I apply this quotient property, I get a bottom that goes to 0. That means the thing is undefined. That's not what it means. It just means that in that case, this property doesn't apply and we can't switch the left-hand side to the right-hand side. We have to use a different tool or technique. So it's very important to be aware of this restriction. And again, it's not that if limit of x goes to g of x equals 0, then the initial limit doesn't exist. That's not what I'm saying at all. I'm saying that if that's true, we cannot use this property. We have to look at the limit a different way. We have to evaluate it using a different technique. But based on this property here, what's a rational expression? Well, that's polynomial over polynomial. If the limiting value is in the domain of f, then that, by definition of the domain of a rational expression and so on, means that the denominator is not 0 there at a. Then we can use this and we just end up with the limit of a polynomial on top over the limit of a polynomial on the bottom. We can apply our polynomial result to get the rational expression result really easy in conjunction with this quotient property. But again, we just have to be very careful when using the quotient property that we're not trying to plug in a restricted value. All right, so some examples. Limit x goes to 3 of x squared minus 5x plus 2. I wonder if I can plug in 3 into this function. Am I allowed to do that by an explicit property or theorem from above? Yes. F is a polynomial. That means I'm allowed to do this plugging in thing. So this is by the corollary. The corollary says I'm allowed to do the plugging in thing. So I can do 3 squared minus 5 times 3 plus 2. 9 plus 2 is 11, minus 15 is -4. If I came over here and did this the old way, let me shrink this down a little bit. X squared minus 5x plus 2. And I'm looking at as x goes to 3. So if I do like 2.99 and so on, I see I get something closer and closer to -4. I get agreement with my kind of empirical way of estimating this. But what I've done here is this is proven. This isn't a guess. It's not an educated guess. It's not a guess supported with evidence. This is what it is based on the definitions and the theorems. This is certainly -4. I mean, provided I didn't make an arithmetic error or something, right? But I'm not guessing it's -4. I'm not thinking that it's -4 based on the evidence or based on the picture. I've proven it's -4 based on the definitions, the theorems, and so on. Limit x goes to 2 of x to the 4th minus 2 over 2x squared minus 3x plus 2. It would be really nice if I could do the plug-in thing here. That makes things a lot easier. Can I do the plug-in thing? Well, I noticed that this function is a rational expression. It's polynomial divided by polynomial. My corollary says that if the limiting value is in the domain, in other words, if when I plug 2 into the denominator, as long as I don't get 0, then I can do the plug-in thing by the corollary. Is that criterion satisfied? Let's try it. Two times 2 is 4, times 2 is 8, plus 2 is 10, minus 6 is 4, which is not 0. 2 is in the domain of f, right? It doesn't give a 0 in the denominator. So therefore, by my corollary, I can do the plug-in thing. I can do 2 to the 4th minus 2 over 2 times 2 squared minus 3 times 2 plus 2. Lots of 2's in this problem. I know that denominator is going to turn out to be 4. I did that calculation already. 16 minus 2 is 14. Or this is 7 halves. Again, I know this is 7 halves. I mean, aside from me maybe making a mistake somewhere or something, but I've proven that it's 7 halves based on the definition of limits and the theorems, the properties that I have above. I could have gotten the same answer. I could have gotten the same answer this way. And if you have extra time on a test or something, it's not a terrible idea to do it a different way and make sure that you got the right answer, that you didn't make some, goofy arithmetic mistake or algebraic mistake or something. Not a terrible idea. 3.5, getting closer and closer to that. Yeah, it looks like it's 7 halves. But again, with the tabular method or looking at a graph or anything like that, I'm kind of making an educated guess. I'm pretty sure that's the result. But here I've proven it based on definitions and theorems. Now this one seems to be pretty similar. Limit x goes to 5 of this rational expression. This is a rational expression, polynomial over polynomial. Can I do the plug-in thing? I might be tempted, but I realize five is not in the domain of f. If I plug in 5 or try to, I get a 0 in the bottom. I cannot evaluate this just by plugging in 5, or I cannot use the corollary to evaluate this. What should I do then? I guess I could go to the tabular method to make a guess, but I would like something more formal than I'd like to take maybe a different approach and see if I can prove what the value of this limit is. Now, something that I have to remember is that if I'm working inside a limit as x goes to 5, x is not equal to 5. I also notice that if I plug in 5 squared plus 5 is 20, or 25 plus 5 is 30, minus 6 times 5, that actually gives me a 0 on top as well. I get 0 over 0. Something like 1 over 0 is undefined. In other words, roughly speaking, it doesn't make any sense. Something like 0 over 0 is indeterminate. This is a very different thing. Indeterminate means if I get something that looks like 0 over 0, it might be undefined. It might not make any sense, but it might be 0, or it might be 10, or it might be negative 100. If I get an indeterminate form, really what I want to do is I want to investigate further. And in particular, one of the main things I look at is there any algebraic simplification I can do? Can I divide stuff out? Can I factor stuff, simplify stuff? to make it no longer look like an indeterminate form. And in fact, here, I know that if I plug in 5 on top, I get a 0. That tells me that x minus 5 is a factor of this polynomial in the numerator. And what do I get? X minus 1 as the other factor. Now here, remember, I'm in the limit, so x is not equal to 5. Apart from x equals 5, this function is exactly the same as the function x minus 1. So we're operating under the assumption that x is not equal to 5. We can do this algebra. We don't have to state a new domain restriction. We don't have a new function. We can divide out the x minus 5s, and I get limit x goes to 5 of x minus 1. This is exactly equal, not equal under some conditions or anything, because the limit carries with it the condition that x cannot be equal to 5. But wait, now I have the limit of just a polynomial. Well, now my corollary applies. Now I have a polynomial, so I can just plug 5 in. I get 4 as the answer. Does that mesh with what I would get empirically over here? I'm looking to plug in values close to 5, 5.01, 5.001. Oops. Help if I put zeros in, and there we go. Yeah, it looks good. I don't know why when I added more zeros, I got a worse result, but yeah, it looks good. But what's the difference? I've proven carefully, formally, that this is the value of the limit. It is equal to 4. It's exactly equal to 4, and I've proven it using definitions, theorems, properties. Let's look at this one, and maybe we'll save this last one for next time. For this last one, we'll do this at the beginning of the next class. Give it some thought, see if you can work through it. It's going to be a similar kind of a structure to the one we just did. Yeah, actually, I'm going to erase that because I think I'm going to need more space to do this one. Now, again, I look at this, limit x goes to 0, square root of 9 plus x minus 3 over x. I might be tempted to do the plug-in thing. There are two problems with the plug-in thing here. The first problem is that this is not a polynomial. It's also not a rational expression because of that square root. So the first reason I shouldn't do a plug-in thing is that it's not one of the few cases, polynomial, rational expression, or just a power function or something like this, where I can do the plug-in thing according to the theorems. That's the main reason I should not try to do the plug-in thing. But if I just kind of thought to myself, just to kind of to guide my intuition, to guide my future steps, if I thought of plugging in x equals 0, what kind of thing would I get? Well, I would get root 9 minus 3, that's 3 minus 3, that's 0, over 0. I get a 0 over 0. This isn't a rational expression, but it feels like there's a factor in the numerator and denominator that should somehow divide out to give me something that I can deal with a little better. What is the algebraic technique I can use to do that? In this case, what I'm going to do, this is a fairly common technique that comes up in these kind of problems. I'm going to multiply top and bottom by this conjugate. Now, one thing that I notice is for this conjugate, when I plug in x equals 0, say in the bottom here, I get square root of 9 plus 3, that's 6. So I don't have that 0 anymore. The other thing that multiplying by the conjugate does is it kind of gets rid of the square roots for me. I get first, the first multiply together is just, oops, this should be 9 plus x plus 3. Should be a 9 plus x under that square root. Make sure to fix that. When I multiply my firsts together, I get 9 plus x. My outers and my inners on the top cancel. I get a plus 3 times root, minus 3 times root. They go away. And then I get a minus 3 times a plus 3 is a minus 9 over x times square root of 9 plus x plus 3. My 9's cancel. My x's divide out. And I'm simply left with limit x goes to 0 of 1 over root 9 plus x plus 3. Now here, this looks a little better. I might be tempted to do the plug-in thing, but again, I don't have anything that says that I can do the plug-in operation for something like this that has a radical in it. That's not a rational expression. So I need to use my properties. I can use the quotient property. I can use some properties of linearity. So I see the limit of the quotient is the quotient of the limits. I get limit of 1 over limit of root 9 plus x plus 3. Limit of 1 is just 1. Limit of root 9 plus x plus limit of 3, but we know the limit of 3 is just 3. Limit of a constant is that constant. Limit of root 9 plus x, well, that's limit of a function to a power, just power 1/2. The power comes out, or the limit kind of sneaks inside of that square root. And then when I have 1 over root limit 9 plus x plus 3, now I have the limit hitting a polynomial directly. Now I can do the plug-in. Limit is x goes to 0. Speeding up here a little bit because we're out of time. I get 1 over root limit of 9 plus 0 is 9 plus 3, or this is 1/6 as the limit. So it's not like if the quotient property doesn't apply directly that the limit doesn't exist. The limit exists here. It's 1/6. You can try the trial and error approach and see that you'll get outputs that are closer and closer to 1/6. We've worked through this formally and carefully using all limit properties. So again, work through this problem. It's more similar to this one. And when we come back, we will continue on with this material.